Welcome to Technovation. I'm your host, Peter High. My guest today is Mike Davies. Mike is the director of Intel's Neuromorphic Computing Lab, a position that he's held since 2017. He's also a senior principal engineer at Intel Labs. We'll talk a bit about the relationship between those organizations. And I also look forward to understanding the basics of this topic and its relevance both to Intel and to the world more generally in Mike's perspective. Mike joined Intel in 2011 as part of an acquisition of Fulcrum Microsystems, where he was the director of silicon engineering. Mike, welcome to Technovation. Great to speak with you today.
Hi, Peter. Great to be here.
Wonderful. Well, let's for the uninitiated or less initiated, I would love to hear in your own words, sort of the definition of the topic. What is neuromorphic computing? Provide some of the basics if you would.
Sure. Yeah. So from my perspective, neuromorphic computing is an effort to go back to the first principles of rethinking computer architecture from the perspective of what we understand today about the workings of the brain, really at the very lowest level. So focusing on neurons and the connections between neurons and the dynamics, the ways that neurons operate at a biological level. And understanding that and adapting that and applying it to the manufacturing, chip design technology we have available today. So as our engineering tool, seeing what lessons, what principles are applicable and try to rediscover a different way of performing computation, hopefully one that is achieving the energy efficiency, the latency, and the adaptability, the ability to learn, online, deployed in the real world with real world data, much better than what we can do today with conventional computer architecture.
And there are obviously a lot of touch points, as you and I've talked about in prior conversations, between the work you're doing and artificial intelligence and deep learning, more generally speaking. Talk a bit about that relationship, if you would. Many people who are watching or listening to this would certainly be familiar with AI and its advances, and perhaps with deep learning and advances there. Talk a bit about the relationship with what you've described and those broader topics as well.
Sure. Yeah. Well, from some perspective, everything is brain inspired in computing. If you go back decades, so 7 decades or more, to Alan Turing, von Neumann, Rosenblatt, some of the very original thinkers in computing and AI, they had the brain in mind. And so they were trying to emulate and capture the amazing intelligence capabilities in the one example we found in the natural world, which was the brain. So all of this has kind of a common family tree, so to speak. Quickly back in those days, there was a divergence between what is now called the von Neumann model, so our standard computer architecture that has advanced by factors of 1 million over the decades, and then meanwhile there's been another splinter, which is neural networks. So really taking this bottom up perspective of let's capture the more literal form that we find in the brain. So back in the 1950s, there was the perceptron, the first kind of hardware neural network. And that's the technology that over decades now has evolved into what we call standard neural networks or deep neural networks, deep learning. And just in the last decade is when we've had the computational horsepower and some of the data set availability to really make that particular approach, which has been decades in gestation, really successful and thriving and now changing the world, just in the last 10 years. But that really traces its roots back to that, 1950s, 1960s era modeling of neural networks, which is an extremely powerful model, but quite different from what we now understand as the way real neural networks, real brain networks operate. So what we're doing is we're taking a fresh look at really thinking about those primitive elements and seeing how they provide capabilities which are very different from what traditional neural networks do in terms of being deployable, operating at very low power levels. As opposed to technology, which is much better suited for, say, data center oriented, very big memory sets, pre-collected data that is, kind of processed through it at once training all the parameters in the network as you do in the sort of the deep learning paradigm, which is incredibly powerful when you have sufficient data and compute to perform those kind of operations, but is very, very different from the kind of learning and adaptation that we find happening in brains of real organisms.
Very interesting. I appreciate that broader background as well. And it strikes me from the way you describe this that some of what you were doing is really thinking long term and the broader innovation that will happen across decades versus the sorts of things that Intel would be able to derive and customers and others would be able to derive value from in the near term. And I wonder, even just from a strategic planning perspective, how you think about that balance between the gains that necessarily one thinks of, for example, eventually getting to artificial general intelligence, which most pontificators would suggest is decades in the future, versus the kinds of advances that have been happening across these various topics in recent years and will continue in the years to come. How do you think about that balance between the near, medium, and long-term implications of what you're researching?
Yeah. So that's a great question. I mean, why now? Even the field, this modern field of neuromorphic computing, where we're really studying modern neuroscience, has been around for some time, even before Intel, invested and got in this area. So really, and if you ask, many in the field, they will answer, neuromorphic computing, of course, is the future, and it always will be, right? So, is the technology ready with the state of semiconductor manufacturing technology that we have? Is it ready to deliver value? Do we understand enough about the way the brain works? And do we have sufficiently advanced manufacturing technology, transistor technology, and related memory technology to really deliver value to the real world? And so that was the top priority. The first question that we were looking at in this research field is to understand what is the state of the art, and given that, how does it compare to conventional techniques, conventional state of the art solutions to the same problems. And that's what the first 3 years of the work with our first neuromorphic chip, Loihi, was all about. Was not necessarily trying to push this out into market immediately, but really to just survey kind of the shotgun-based approach of all the different possible applications where this might be deployed, and where does it outperform conventional solutions? Where does it not? Where do we need, ongoing innovation in transistor scaling, new memory technologies? Where is the algorithmic understanding of how these brain systems work? Where is it just, too early to really do something useful? And so that's what we've been engaged in over the last 3 years, and we have a pretty good understanding that there's a range of applications. Some which are quite viable in the near term, and there's a growing ecosystem of startups that are really tackling some of that near term opportunity. And then there's the longer term. You mentioned artificial general intelligence, right? These are not things that are happening overnight. I think myself and those in the field feel very strongly that eventually neuromorphic architecture will be part of that answer, an essential ingredient if we want to capture the kind of intelligence that we observe in humans, and scale that up even larger potentially. But we don't have to wait to figure out and answer all those problems. We are finding applications and value in the near term at a variety of timescales.
Well, Mike, I appreciate you walking through the interesting ways of thinking about both the near-term opportunity and the long-term opportunity associated with this topic. I know from our past conversations, although there has been tremendous progress made in terms of computing power, in terms of data sets, in terms of a variety of things that are coming together that have allowed for further advances in artificial intelligence, deep learning, and certainly, of course, neuromorphic computing. But that there are a lot of challenges that still remain that impede the progress and are challenges to overcome. One thinks of further technology challenges in addition to cost challenges. I wonder how you think about those things and some of the approaches you've contemplated to overcoming them.
Yeah, sure. So I would say, you can break the research challenges down into maybe 3 general categories. One is, can we build the basic hardware architecture that is capturing what's known from an algorithmic perspective in an efficient, performant way, and kind of build something that's functional, basically, from a hardware perspective. There's then the software challenge of making that useful. So developing, kind of rethinking computation and algorithms and the entire software stack that has to sit on top of this very exotic new computer architecture. And then there's kind of some of the fundamental issues related to, given our current transistor technology, our current semiconductor manufacturing technology, what does that add up to as far as an overall, total cost of ownership, trade-off for a customer for a particular application. And I would say on the first challenge there, things are looking pretty good. So although, of course, we don't understand everything about the way the brain works and algorithms that can provide value, there's enough understood that we can certainly build some of these, build accelerators, build chips like we have with Loihi that perform pretty well. And so that, I would say, from a basic hardware design and architecture perspective, things are kind of almost green light. Now, on the software perspective, because it truly is a rethinking from the bottom up, we're lacking an ecosystem of developers. Where even in the deep learning world, you have tens of thousands of software developers, if not hundreds of thousands now, that really understand all the nuances of the available computer architectures, the algorithms, and can immediately deploy this into real world applications. But in the neuromorphic world, the basic idea of computing is different, and the way you think about coding and constructing networks is really has to be rethought. And so that's a major challenge we're facing, which is going to limit the commercial deployments to pretty niche opportunities. These are not going to be general SDKs that are put out that can allows applications to really unlock the true value of the technology. It's going to be more targeted point solutions in this kind of foreseeable few-year future from here. And then the last one is unfortunately pretty fundamental based on where we're at today. One of the central defining properties of neuromorphic computing is the co-location, the very tight integration of computing or logic gates, kind of the arithmetic and multiplicative and all these kind of logic operations that are associated with processing data with the storage of data itself. And that in the brain is happening at the level of an individual neuron. And there are 80 billion neurons in the human brain. So there isn't a separate, to put it in concrete computing terms, there isn't a separate DRAM or a hard drive and the processor, CPU. These two concepts, these two architectural ingredients are completely smushed together and weaved into a neural fabric. And our manufacturing technology just isn't set up for that. The entire semiconductor industry is partitioned between memory manufacturing and logic, compute manufacturing. So that means what that translates to, bottom line, is an increased cost, per function for neuromorphic chips. Because we have to use one of these processes or the other, and due to the complexity of the computation, it has to be in the compute process, and that means that the cost per storage unit, the per data unit of that's stored inside this chip, is at the cost of SRAM or the embedded memory that's in these logic processes compared to the cost of DRAM. So that's a pretty fundamental headwind, I would say, that the field faces. And what that means is that neuromorphic applications tend to be quite small scale. So they're intended for deploying into edge devices, maybe small accelerator functions in standard SoCs for audio processing, low dimensional kind of problems where you don't need the resources of very large data sets, very large network processes like vision, complex scene understanding, and database analytics and these kinds of things because the cost is prohibitive, basically.
Very interesting indeed. Well, I know that you joined Intel via Fulcrum Microsystems, a company that was acquired by Intel. Fulcrum Microsystems itself was born out of Caltech, where you have multiple degrees. And so the the sort of foot in the academic world and the importance indeed of the academic world and the research that comes from it, oftentimes that is many decades, looking many decades into the future with less of a profit motive associated with it necessarily. This whole concept of the broader ecosystem and building one in order to deliver what you have described, Mike, is clearly an important aspect of what ties all this together. And in fact, the whole topic of neuromorphic computing, as you point out, as it replicates the functioning of the brain, it really involves a lot of disciplines that need to also come together as an ecosystem in order to deliver this. Talk a bit about the way in which you've thought about curating that ecosystem to deliver what you've described.
Sure. Yeah. So engaging with the academic community is an essential part of the successful progress in this field. And that's not necessarily unusual for Intel Labs. I think many other groups within Intel Labs has vibrant engagements, collaborations, and we fund a number of academic groups around the world across all the areas of research that we pursue. But what is really unique about neuromorphic computing is that multidisciplinary aspect. So we're literally working with neuroscientists. Like we don't go into labs and work with biological neurons, but we collaborate with academics who actually do that work on that wet science side of things, and that's pretty unusual for semiconductor company research groups, right? And at the same time, we're not looking to simply copy what we see in the lab in biological organisms. Ultimately, we're trying to understand the principles. So reduce this down to understandable math, models, and so for that reason, we're quickly steering in the other direction, which is theoreticians working with mathematicians, physicists, even, and of course, computational neuroscientists that can really, take these observations that come from biological neurons and condense this down into simple theories. And then everything in the middle. Of course, we also have to work with the conventional computer scientists, the computer engineers, even design methodology research. So although we at Intel, we're sticking to a digital style of neuromorphic chip design, which is using, by and large, standard industry tools, standard methodologies, there's still some very unique aspects of that. So asynchronous design, for example, which is actually what we carried forward with us from those Fulcrum days. That was our technology there that came out of Caltech. We still have collaboration and research into this different style of designing digital chips, which is clockless. This is unlike what nearly all commercial chips today are using. Synchronous design. We're using something different. We're taking that clock out, and that's much more the way the brain operates, where information is signaled through events, these spikes, action potentials, and the timing of those spikes or these packets are actually encoding information along with the data that it carries itself. So across all these ranges, there's a great deal of collaboration, and we have a community that we've been building over the last several years to sort of formalize and structure this collaboration and really provide a way to give people access to our neuromorphic chips, which are research chips. We're not selling these at all. We give this access free to the community, and that's grown out to over 150 groups around the world. Mostly academic, but of course, that's not our end goal. We love to work with the academics, but increasingly we're working with government labs. That's a very important ingredient there too, where they have the resources to make bigger investments in these projects that with long time horizons. And then also more and more corporate groups. So the customers of Intel that are coming with problems that are not well solved yet with standard methods, and there's not necessarily a clear path to how you get to the types of solutions that they need. And neuromorphic technology might be offering the solution. And so these are some of the most fun engagements because we got to really think about how this technology can impact the world and solve problems that are just not possible to solve yet.
Interesting, Mike. Well, you've mentioned a couple of times Intel Labs. Your neuromorphic computing lab is part of the broader Intel Labs, and I've had the pleasure of speaking with a number of people at Intel Labs, including Rich Uhlig, the director of Intel Labs. Talk a bit about the relationship between your lab and the different component parts of Intel Labs, and frankly, also the the way in which you all work together. I'm sure that the Venn diagram that applied across the various parts of the lab has quite a bit of overlap. Just as, of course, there are some aspects that are unique to one group versus the other. Talk a bit about the ways in which you and your peers across the lab work together, please.
Sure. Yeah. I mean, as you can imagine, that Venn diagram is very complicated. I mean, Intel's business, it touches all aspects of the real world, of all, technology. So Intel Labs mirrors that. We have research in all areas of computing, and so it's a really fun and dynamic environment because there is that diversity across the entire scope of computing. Now, neuromorphic computing, my lab, Neuromorphic Computing Lab, is engaged in pretty much the most, about as basic an area of research as Intel Labs engages in. So this kind of quite a long time horizon, thinking about, really rethinking the basic principles of computing. That's not so common necessarily in Intel Labs. There's maybe quantum computing is the one other analogy of where that kind of rethinking is happening in a kind of fundamental approach. Now we're compared to quantum, we have a sort of enviable position where we have chips today. We have a technology that's, from a hardware perspective, could be commercialized. So that means we do have a lot of collaborations, not just outside the company with academics and government groups, but within Intel Labs, with other people pursuing more conventional approaches to AI, applying AI tools that are available today to problems, both inside Intel and outside, our customer problems. And so they provide a really, close, insight into some of the struggles that we have with conventional AI technology, conventional architectures, and so we can, collaborate very deeply and think about, fundamental competitive advantages that we can offer, for Intel, facing those kinds of challenges.
Excellent. Well, Mike Davies, thank you so much for taking time with me today to speak on Technovation about the groundbreaking research you and your team are doing, giving us a bit more context to neuromorphic computing and what we might see in terms of progress in the near term versus the long term, and just the more broad view that you have in terms of how to bring all of this to life. It's been a really interesting conversation.
Sure. Yeah, it's been a pleasure. Thanks, Peter.